Hello and welcome. This section is a review of basic concepts in atomic physics and nuclear physics. These concepts represent a basic important knowledge for any inspector at FANR. The material that we are going to review and will not be discussed in detail is the composition of the atom and the basic properties of the components of the atom and the nucleus, instabilities in atoms and reasons for transformations and radioactive decays, the three basic modes of decay, and the two most important nuclear reactions. We will also introduce and review the concept of activity. Activity is a very important quantity in radiological protection. If you are familiar with these concepts, you can skip this section. If you are not familiar and you need to go a little bit more in detail, I suggest you have a look at any textbook in nuclear physics. This textbook, which is very much used in the UAE, in Atoms, Radiation and Radiation Protection by James Turner. This book has the initial chapters, as many other textbooks, devoted to these concepts. So, for example, in the chapter 1, there is a discussion about atomic physics and radiation. Chapter 2 is the atomic structure and atomic radiation. Chapter 3 is the nucleus and nuclear radiation. And chapter 4 is radioactive decay. We will be following more or less the same structure. Again, this is just a review. If you are familiar with this material, you can skip altogether this presentation. This section is called Some Unavoidable Physics. Matter is composed of atoms. Atoms are basic building blocks composed of an internal nucleus, which is made of so-called nucleons, that is, protons, which are charged positively, and neutrons, which don't have an electric charge. The size of the nucleus is around the size of a Fermi, that is 10 to the minus 15 meters. Around the nucleus is a cloud of orbiting electrons, which are in the same number as the protons, and they make the outside structure, the outside shell of the atom. The order of magnitude of the atom is the angstrom, that is 10 to the minus 10 meters, or 100,000 times larger than the nucleus size. The conclusion is that most of the atom is composed of vacuum, of empty space, the nucleus being a very small component compared to the size, to the external size of the atom, although within the nucleus, the vast majority of the mass of the atom is contained. Normally, atoms are characterized by an atomic number, which indicates the elemental family. This atomic number is the number of protons or the number of electrons, which is the same. Protons and electrons, they are in the same number. There is another number, which is called neutron number, and is normally indicated with the letter N, while the atomic number is indicated with the letter Z. The number of neutrons plus the number of protons, the atomic number, is the mass number, which is indicated as A normally. The chemical properties of an element and its family, they come from the characteristic number of proton and electrons. Therefore, we can say that the chemical properties of an atom depend on Z, while the nuclear properties of an atom depend both on its atomic number and its mass number. The varying number of neutrons makes the family of isotope of a specific element, which are components of the same elemental family, having different physical characteristics and nuclear characteristics as well. Normally, in nuclear physics, these numbers are positioned around the chemical symbol of an atom. So if we take the uranium as an example, its chemical symbol is U, and its atomic number, it's 92, which is normally positioned on the bottom left of the symbol. The mass number, 235, in this specific example, is positioned on the top left, while from time to time the number of neutrons, is also present. It's indicated on the right side, either on the top or, more frequently, at the bottom. In many cases in nuclear physics and in our applications, a specific isotope is indicated only by its chemical symbol and the mass number. So it will be uranium 235 without indicating neither the number of protons, which is already given by the family, by the chemical family, nor the number of neutrons that you can obtain if you know the Z. Now, just one word related to why isotopes are called like that, and the classification of elements and isotopes. So, you know that the classification of elements has been developed in the past centuries, and it is normally structured into the so-called periodic table of elements. This is the table, Mendeleev table, in which each single element is contained in a case. So we have hydrogen here, we have helium, we have lithium, beryllium, and so on. And at some point, we also have uranium, plutonium, americium, californium. These are very, very heavy elements. Now, this classification has, for each case, just the chemical element. So the fine structure, let's say, of the isotopes, which are elements having the same, of course, atomic number, but a varying number of neutrons, that fine structure cannot be represented in this table. The table which is used for the representation of the isotopes is the so-called table of the isotopes or nuclide chart. And there are a few nuclide charts around the world. They share the same design and the same idea. And the idea is that each isotope is positioned in this kind of graph according to the Z number and the N number, or the opposite on the x-axis or the y-axis. So, for example, in this table, in this specific table, the Z number may be on the x-axis, and the number of neutrons, N, may be on the y-axis. This table is much bigger. The number of cases is much higher than the cases in the table of the elements. Therefore, normally, these tables are broken into chunks. And to represent the whole table, you need a very large surface, as it is the case here in the Karlsruhe Institute of Technology, the KIT, which is one of the institutes developing a very famous table of the isotopes. A few words about the particle composing the nucleus and the atom. Protons, basic components of the nucleus, are subatomic particles, nucleons, which are also baryons and fermions. this additional information is not essential for us. They are indicated as P or P+. They bear one electric charge, one positive charge, and their mass is a little bit more than 1 atomic mass unit, or around 1000 megaelectron-volt over c squared. They have an internal structure. They are composed by 3 quarks, and they were discovered only in 1920 by Ernest Rutherford. The neutron, which is also a nucleon, a component of the nucleus, and also is a baryon and a fermion, is normally indicated as N or sometimes as N0 to stress the fact that it doesn't have any electric charge, it is neutral. Its mass is very similar, although a little bit bigger than the mass of the proton, and it's again around 1000 megaelectron-volt over c squared. Also, the neutron has an internal structure, and it's made of 3 quarks, and it was discovered even later by a famous experiment in 1932 by James Chadwick, quite late in the history of nuclear physics. Electrons, they are completely different. Electrons are elementary particles. They don't have an internal structure, and they obey to different characteristics. They are leptons, and they are fermions as well. They are different particles than protons and neutrons. They are normally indicated as E or E minus to stress the fact that they also carry one charge, which is a negative charge in this case. Their mass, this is very important, their mass is very small. It's almost 1 over 2,000th the mass of the proton, and indeed it's much easier if we just remember their mass in terms of MeV over c squared, because their mass is 0.5 megaelectron-volt over c squared. So if you remember the mass of the proton and the neutron, which is around 1000 megaelectron-volt over c squared, the electron has 0.5 megaelectron-volt over c squared. It's also useful to remember 500 kilo-electron-volt, because this is a very, very typical energy ray in a spectroscopy analysis, and we will come to this whenever we discuss the radioactive decays. But it's good to remember 511 kilo-electron-volt, or half a megaelectron-volt over c squared for the mass of the electron. The electron doesn't have an internal substructure, and it was discovered quite early in the history of atomic and nuclear physics, at the end of the 19th century, with another very famous experiment by Joseph John Thomson. It's very important to remember that forces within atoms are very big, and there are basically 4 important forces. Well, the first one is the electromagnetic force of Coulombian nature, which is repulsive for charges and particles of the same sign. So protons and electrons tend to repel each other, but they are attractive for particles of different signs. So protons and electrons, they tend to attract one to the other. The Coulombian force is strong and stronger when the distance reduces. It depends on the square, on the inverse of the square of the distance, so its magnitude increases when the distance decreases. Now the question comes, how come protons can stay together in the nucleus, which is a very small volume of the order of 1 Fermi in size? How can they be packed in such a small volume? The reason is that there are also other forces within the nucleus, and specifically the force which is keeping together protons and neutrons in the nucleus. It's the so-called nuclear force, the strong force. This force is attractive for all the nucleons, so protons and neutrons, and its magnitude is much bigger, almost 100 times stronger than the electromagnetic force at those same distances. Although one characteristic of the strong force is that it operates only at very, very small, very short range. There is another nuclear force which is called weak force. This is the force which keeps together the quarks inside nucleons. It is again an electromagnetic force, and it is the force which is behind the transformations of, for example, a proton into a neutron and a neutron into a proton, that is the beta decay. We cannot forget that also gravitational forces exist within the atom and between atoms, because masses tend to attract each other according to the gravitational law. But this force, which is, yes, attractive, it's absolutely negligible at these distances. So we can absolutely forget about it. You may know that in the history of nuclear physics, there have been several atomic models and nuclear models. The latest and the most accredited today is the so-called Schrödinger atomic model of quantum mechanics. And in this model, electrons, they orbit around a massive central nucleus again, but they are not in orbits which are clearly defined and predetermined. They are sort of delocalized in electronic clouds, and they are represented by wave functions. It's possible to indicate a probability where an electron will be, but it's not possible to indicate exactly where it will be at a specific time. So in this representation here, for example, the density of probability of that wave function is indicated as increasing shading of gray, which means that there is a higher probability in this volume, in this area, around the nucleus, that the electrons will be in this volume here, and there is a diminishing probability that the electrons will be at bigger distances from the atom. And at some point, the wave function goes to zero as well. That is, there is no probability at distances which are much bigger than the atom size. In this model, as we have already discussed, the atom is represented as being the order of 10 to the minus 10th meters, and the nucleus of the order of 10 to the minus 15 meters. In order to better understand what is the driving force behind radioactivity, we have to think about balances of stability and instability within a transformation. Changes in isotopes, and notably the changes which lead to radioactive decay, the radioactive transformation, are originated by instabilities in that specific isotope. And the change is a quest for better stability. So let's have a look at how atoms and nuclei are kept together and how these forces change when a transformation happens in the nucleus. We need to talk about binding energies. You may remember this graph at the bottom. This graph represents the binding energy per nucleon, depending on the mass number of a specific radioisotope. Let's have a look at this graph. This is the binding energy graph. And we can see a few things just by looking at this graph. The first one is the binding energy per nucleon in megaelectron volt per nucleon all across the board is comprised between 7 and 9 megaelectron volt per nucleon for most radionuclides, with some notable exceptions only for lighter nuclei. Now, among the lighter nuclei, there is one which stands out, and that's helium-4. And this, we know, it's a very strong, very stable aggregate. 2 protons and 2 neutrons. It is indeed also the alpha particle. Something else we notice here is the binding energy increases until reaching a maximum around iron, and then it decreases steadily. Here we have two important considerations. It's possible to generate energy by fusioning together lighter nuclei into a heavier one. And in that process, there is a mass defect which is released as energy. This is the basis for the fusion nuclear reaction, and it is the way energy is generated in stars and will be one day generated also in fusion reactors. Exactly the same way, splitting a heavier atom into two smaller chunks, it's again an energetically viable process and generates energy. Now, we will make a calculation in a separate exercise to show how this works and how much energy is obtained by splitting an atom into a fission nuclear reaction, or by putting together, fusioning two atoms into a heavier one. But this curve is very important because it shows the theoretical possibility to generate energy by splitting heavier atoms or by fusioning smaller ones. Now, in transformations which happen spontaneously in radioactive decay, we should have an understanding of why transformations happen and what is the final result of those transformations. By plotting all the radionuclides in nature into a curve, and this graph is called the stability valley, we will see why, we can already see one important element here. Now, the radionuclides are in this graph put in terms of neutron number n on the x-axis and on y the proton number. What we already see is for the majority of them, they lie in an area where there is an excess of neutrons than protons. So we have understood that neutrons add strong nuclear force binding together nucleons in the very small volume of the nucleus. So somehow in nature, heavier aggregates can stay together only because there is an additional number, a higher number of neutrons than the number of protons. For smaller, lighter nuclei, the number of protons and neutrons is very similar. But as soon as we go up in the mass number, as you can see here, the greatest majority of radionuclides lie in this part of the diagram where there is an excess of neutrons. Something else we also notice here is the fact that there is a color code in this graph. Now, the color code is also important. You can see that the greatest majority are either red or blue. And in between the two, there is more or less a line which is black. Now, you should imagine this as a valley. And at the bottom of the rifts of the valley, there is the Stability river, which is black, because these nuclides are the ones which do not undergo any transformation. They are either stable with time, or they transform in times which are much longer than the times scales of the universe. So we consider them stable with time. All the others, they do undergo changes. Now, the changes undergone by the blue ones is a reduction in the number of neutrons and an increase of the number of protons of 1 unit. So the mass number doesn't change in these transformations, just neutrons decrease by 1 unit and protons increase by 1 unit. And the same is true for the red transformations here. All these radionuclides indicated as red in this graph undergo transformations which reduce the number of protons by 1 unit and increase the number of neutrons by 1 unit. These are called beta decays, beta minus and beta plus. And the beta decay is a transformation in which the mass number stays the same. So what happens to radionuclides on the rifts of this valley, the blue rift and the red rift? That these radionuclides, they roll down from one case to another one, to another one, to another one, following always the line of the same A, of the same mass number, and they fall down to a black, stable river case in the Stability Valley. Now, what happens to the heavier ones, which have a different color? They are yellow, indicated as yellow here. Well, they undergo more fundamental transformations, which are typical, as you can see, for heavier nuclei. So the yellow transformation, which is the alpha transformation, happens only for big radioisotopes, because it's a more dramatic transformation, as we will see in the atom structure. Here, the mass number is not conserved. On the contrary, it is dramatically changed by 4 units. So this graph allows us to understand what is the quest of radionuclides toward a more stable configuration and how this quest is operated by virtue of beta decay and alpha decays. And now we will have a look, more closer look to these two transformations. The beta decay, as we have said, is a transformation of a neutron into a proton or of a proton into a neutron. These transformations, they operate in these two directions. Beta minus, the transformation of a proton plus a beta minus particle, which is an electron, and an antineutrino. Beta plus, the transformation of a proton into a neutron. A positive electron, which is the antiparticle of the electron, is called positron or beta plus, and the neutrino, which is the antiparticle of the antineutrino. Now, neutrinos and antineutrinos are not really important for us in terms of radiation protection, but they are important to understand one important characteristic of the beta decay. The beta decay is a 3-body transformation, which means that in the beginning there is only one nucleus. At the end of the transformation, there is a different nucleus. There is a beta particle, either beta plus or beta minus, and a neutrino or an antineutrino. So these 3 particles, they share the energy and they share momentum, and there is a multiplicity of possibilities, because a beta particles can be emitted in one direction, and the neutrino, to compensate momentum, can be emitted in the other direction. So, due to the fact that this is a 3-body process, the energy of the emitted beta particle is not fixed in this transformation. On the contrary, it is a continuum going from 0, when the beta particle is emitted with no kinetic energy, up to the maximum energy of that transformation, the Q value of that decay. And as you can see here, there is a probability that the energy of the emitted beta particle is a specific value, and the maximum of this curve, in this specific example, which is the example of carbon-14, is around, as you can see, a maximum decay is around 160, 150 kilo-electron volt, and the maximum probability is around 50 kilo-electron volt. This is an important rule of thumb. Indeed, the most probable energy doesn't depend automatically from a parameter, but from a series of parameters. It depends on each decay. But as a rule of thumb, it's easy to remember for us that the most probable energy is around 1/3 of the maximum energy of that decay. So we can write this way, and this is useful to remember, especially when we need to do calculations of shielding of beta particles, or maybe choosing a specific detector or the efficiency of a detector. Another important aspect of beta decay is the destiny of the positron. Now, what happens to beta minus and beta plus is more or less the same fate. They are very light particles, They interact strongly with the surrounding medium. They are bounced back. They have strong interaction with much heavier nuclei. And eventually, the beta particle is absorbed by the medium. It's one additional electron in a sea of electrons. This is not the same for the positron, because the positron is the antiparticle of the electron. So eventually, the positron will meet an electron, and the two of them, they will annihilate, so they will disappear, and two gamma rays of the same energy will be created in that point and will be emitted in opposite directions. Now, this is very important. This is not science fiction. This is something we see every day because it has a very, very important application in the practice. So you remember when we said that the energy of the beta particle is 511 kiloelectron volt? Well, in this transformation, when the two particles annihilate and disappear, the two gamma rays, they have exactly that energy. So the two characteristic gamma rays of 511 kiloelectron volt are the signature of this annihilation. And if we are able to identify and determine the direction where they come from, we are even able to see where the actual transformation took place. Now, the reason why I'm going in these kind of details is because this is a very, very important application, and for some inspectors is also one important facility to inspect. That's the principle of the positron emission tomography, or PET analysis, which is a diagnostic technique in which a radionuclide spiked with fluorine-18, beta plus emitter, is injected into a patient. And this beta plus emission generates two gamma rays emitted in coincidence in the same direction, and an array of detectors positioned all around the patient allow to determine in coincidence where these two gamma rays are coming from, and by measuring the slight time difference in the arrival time to determine where on that direction the emission took place. So it's possible basically to determine the distribution of the beta plus emitting radionuclide in the patient, allowing for a very detailed diagnostic image of even a small cancer formation. These kind of machines is PET tomographic machines are used for these analysis, and they are available in the UAE. The FDG, the fluorodeoxyglucose, which is marked with fluorine-18, is either produced at the same facility in the hospital or it is transported and bought. It has a half-life of around 2 hours, which is short enough to disappear in the body of the patient after 1 day or 2. So reducing the hazards for the patient himself and for the surrounding family and friends. But it's long enough to transport it, to manufacture it, transport it, inject it to the patient, measure it. So it has been chosen as a convenient balance between short and longer half-lives. So quite an important application of the beta plus decay here. Alpha decay, as I mentioned, is a very dramatic transformation for radionuclides. If beta decay, they do not change the mass number of a radionuclide, well, alpha decay does. First of all, alpha decay happens only for those radionuclides who are very heavy. In the area of the diagram here, which is indicated as yellow, normally for radionuclides of mass numbers of 200 or above. Now, if we consider a generic radionuclide, X, the transformation leads to a Y radionuclide having 4 mass numbers less and 2 protons and 2 neutrons less, and the aggregate which is emitted is either the alpha particle or is called helium-4 nucleus. Of course, there is a Q value in this reaction. Now, the reaction is a two-body process, so it's possible to calculate how the energy is split between the alpha particle and the recoiling alpha-emitting nucleus. We will do this calculation in an exercise. This very dramatic transformation is a very efficient way for radionuclides to lose mass. While beta transformations, they don't allow the radionuclide to change mass, alpha transformations, they do. A third very important transformation is the gamma emission. Gamma emission is not specifically a radioactive decay. It accompanies other radioactive decays because normally a decay process is quite complex, and the arrival point after the beta or alpha transformation is not the fundamental least energy state of that radionuclide. It's normally a higher energy configuration, so the nuclides need to lose that excess energy, and will do that by releasing a chunk of energy in a photon of gamma emission. Now, gamma emission is normally accompanying another decay process, but in some notable cases can happen by itself after a significant time. We call these metastable states. It's not formally a radioactive decay process, but it's understood better as a de-excitation of a nucleus. Now here we have a notable example, the beta decay of cobalt-60 leading to nickel-60. Cobalt-60 is a typical activation radionuclide in nuclear reactors, and you will find it in waste management, in decommissioning activities. And the characteristic here is the emission, not only the beta minus, but the two characteristic gamma rays which accompany this emission. And as you can see from this diagram, going from this stable, well, unstable state of cobalt-60, 99% of the times to this excited state of nickel-60, nickel-60 decays by emitting two gamma rays, one after the other. And it's also, familiar for those who do those spectra analysis. It's 1173 and 1332 kilo electron volts. These are the two energies of those gamma emissions. In a very rare number of cases, less than 1%, the transformation from cobalt-60 goes directly to this energy level with the emission of only one gamma ray of 1332 kilo electron volt. So these two gamma rays are a sort of signature for the radioactive decay of cobalt-60, and they are actually sought after when you do spectra analysis looking for the presence of cobalt-60. What are gamma photons? Gamma photons are electromagnetic radiation, as much as radio waves and visible light. So if you consider the spectrum of electromagnetic radiation, you can express this either in terms of wavelength and or in terms of energy, and the two are one the inverse of the other. So lower energies correspond to longer wavelengths, and shorter wavelengths correspond to higher energy. So if you go from the less energetic to the highest energies, you will find radio waves, then microwaves, infrared radiation, visible radiation, which is a very small part of the spectrum, visible light, then ultraviolet, X-rays, and gamma rays. Now, gamma rays and X-rays are the same thing. It's just electromagnetic radiation of different energies, but the reasons why they are called differently, it's due to the historical reason. We want to indicate the origin of these emissions. X-rays are the result as a de-excitation of the atom. So, for example, when the atom is ionized, it loses one electron. There may be a rearrangement of electrons in the structure of the atom. And one transition of an electron from an energetic level to a lower energetic level is accompanied by a corresponding energy of an X-ray photon being emitted as well. So we have it here. If the delta energy, the difference between the two levels is indicated as delta E, This will be the energy of the emitted X-ray, so the H constant multiplied by the frequency of that radiation. So X-rays can be generated by spontaneous transformations in the shells of the atom, while gamma rays are generated in the nucleus by nuclear transformations. But X-rays can be generated also by another mechanisms, that is, charged particles which are decelerated in a medium. They irradiate X-rays. This is called, in German, Bremsstrahlung, and it's a type of reaction. It's a terminology which is used very much all around the world. That means breaking radiation, Bremsstrahlung, breaking radiation. So, first of all, we can make use of this by sending particles into a medium and let them decelerate in that medium. We can create X-rays, but X-rays are also naturally, spontaneously created whenever a beta particle is emitted. Now, how to distinguish between the two? First of all, spontaneous X-rays coming from the de-excitation of electronic levels in an atom have characteristic lines as much as gamma rays are the fingerprints of a transformation in the nucleus. But this is not necessarily true for X-rays coming from Bremsstrahlung. There is a continuum of energy. Well, there are some signatures also in that continuum, but mainly we can say that there is a continuum of energy in slowing down electrons in a medium, and it is possible to generate, at least theoretically, any energies of X-rays. So that's the reason why also it's not true in the representation that we have seen before of the spectrum. It's not true that X-rays always have energies which are below the gamma rays. It may be possible that gamma rays have lower energies than some X-rays, especially generated X-rays by Bremsstrahlung. The reason why they are called X and gamma is to identify the origin, where they are created from. X-rays can be spontaneous, generated by transformations in the atom, or generated by the Bremsstrahlung of beta particles. This is important because beta sources, as you will notice, are normally housed into containers which are designed to minimize the generation of X-rays by Bremsstrahlung. If you put a beta source in a lead container, it will maybe shield the beta particle itself, but it will create X-rays in exchange. That's the reason why plastic, which is a lossy hydrogenated material, is normally used in order to shield beta particles emitted by a beta source. We can, by using X-ray machines, generate X-rays of specific energies by accelerating electrons to a specific energy and then letting them slow down in a target. What happens then? The beta particle or the electron comes with a certain kinetic energy. In the interaction with the nucleus of the target, changes direction, loses kinetic energy, and the difference as balance of energy and momentum is an X-ray, a Bremsstrahlung X-ray, which is generated, in this case, in this direction. This is the basic functioning of an X-ray machine. Just a few words about rarer phenomena. One is the neutron emission. There are some transformations which lead to the emission of a neutron. They are quite rare. This is one of them. Krypton 87 metastable transforming into krypton 86 by the emission of one neutron. Quite a rare process in nature. What is important, just for our culture, our nuclear culture, delayed neutrons are very important in fission products, and they are very important in the nuclear reactor for nuclear physics, both for criticality control and for reactivity. So they are very important in the balance of energy in the fission equation. but they are not specifically important in radiation protection because they are normally confined within the reactor and they are not of specific radiation protection interest. And so is spontaneous fission. This is quite a rare process. It can happen in very, very heavy nuclei, and it is, again, a very dramatic transformation in a structure of a nucleus. There are just a few radioisotopes which transform naturally by using spontaneous fission. One of the most notable is californium-252, but there are others as well, various isotopes of very heavy elements like curium, plutonium, thorium, protactinium, and so on. Just to remember, these fission spectra are different, neutron fission spectra are different than the induced fission, like the spectra you will find in a reactor. Let's come to a conclusion by introducing a very important concept, which is the concept of activity. The activity is defined of the number of transformations which happen in a sample by unit time. Activity is defined like that by considering that the number of transformations in a given sample is always the same, and it is a constant, a physical constant, specific to that radionuclide and that transformation, which is indicated as lambda, the disintegration constant. So we can say that the number of transformations over a certain number of nuclei is a constant, a disintegration constant multiplied by the unit time. Or by rearranging this equation and defining activity as lambda multiplied n, we can describe it in terms of activity. Activity is a quantity which indicates the number of transformations, not necessarily the number of radiation which are emitted. If in one transformation, remember the cobalt-60, there is more than one radiation which is emitted, well, one transformation will lead to more than one emission of radiation. The number of transformation is expressed in a quantity which is called, in the international system, becquerel. Now remember that units are written small caps, even names like becquerel, but when you use the actual symbol, B is a capital B and Q, BQ. This is a special unit because it is a frequency, it's a second to the -1, it's a rate like hertz, but it's a specific rate which is used in nuclear physics only. In the past, important to remember, activity was expressed in Curie, again, small c in Curie, but capital C when you write a symbol. This quantity is very big. It's equivalent to 3.710 to the 10th becquerel. And it is an obsolete unit which should not be used anymore, although still quite very popular in some cultures. The UE have adopted the international system, so the unit for activity is becquerel, 1 disintegration per second. Now, if we integrate the equation, the previous equation, we can express the number of nuclei, or multiplying by lambda the activity, as the original number and 0 multiplied by the exponential of minus lambda t. Now this is very important because we can obtain from this expression two important considerations. The first one is, due to this fact, to this exponential, decreasing exponential, the number of radionuclides, and the activity is decreasing with time. It goes down with time. And we can define a specific parameter which indicates how fast this is decreasing, the speed at which the radionuclide disappears. We define this speed as half-life, the time which is needed for a certain quantity of radionuclide to become half, or for a specific activity, for a specific number, to become half of it. We will see in an exercise how to obtain half-life as a relationship with lambda. It's very simple and straightforward. But remember, half-life is a parameter which is very useful in the practice. It indicates the speed at which the disintegration is taking place, and it is specific to that radionuclide disintegration in that mode. So if one radionuclide is, say, for 90% of the cases decaying alpha, and for 20% is decaying beta minus, so it has two different branching ratio, there will be two different half-lives for these two disintegrations. Where do you find these numbers? You will find them in the table of the isotopes, and we will see that later. Another brown slide, why this is important, to give you a rule of thumb. Let's remember that the half-life is a practical quantity. One half-life means half of the original activity is gone. So 2 half-lives means 1/4. 3 half-lives means only 1/8 remains. Okay? So how can we know when around 100 of the original activity only is remaining? Well, if you do this calculation, 2, 4, 8, 16, 32, 64, 1/28, you will notice that after 7 half-lives, around 100th of the original activity remains. And after 10 half-lives, around 1000 is remaining. So if we have fluorine-18, for example, disappearing with 2 hours half-life, after 2 hours, there will be half of the original quantity. After 7 multiplied to 14 hours, there will be 100th, actually less than 100th remaining. And after 2 multiplied 10, 20 hours, there will be 1000 remaining. So it's quite easy by using this rule of thumb to have a quick indication of the rate at which radionuclide is disappearing, and also make a quick calculation of the residual activity after a certain time. We have concluded our review of atomic physics and nuclear physics. These are basic concepts which represent a foundation for knowledge for any inspector. Most importantly, in this section, we have seen where radiation comes from and why radiation is emitted by atoms. As a quest for a better stability, these transformations bring the atom in a configuration which is more stable than the previous one. We have also introduced very briefly 2 important nuclear reactions, fusion and fission, that can be used to the advantage of humanity for the production of electricity. At least theoretically, the fusion reaction, which is currently very much researched in the world, and practically, the fission reaction, which is used in so many hundred nuclear reactors around the world, and in the 4 power stations in Baraka. In the next chapter, we will review the interaction between radiation and matter.